Okay, so we're talking about similar solids and complex solids today. We're going to just do the first part of complex solids, and then next time we'll do the rest of complex solids. Okay, so looking at these two prisms, I want to know, are these two prisms similar? We've talked about in the past how to look at two shapes and tell if they're similar or not, and we know that we have to set up a series of proportions. So when we do this, we compare the same pieces of the prism in order to see if the proportions are similar. So I'm going to compare the heights, the height to height, the width to the width, and the length to the length. So I'm going to start out by noticing I have my height here and my height here. So when I do that, I'm going to say, okay, 4/9. Is that equal to my widths? So that would be 3 to 8. And then lastly, we're comparing our lengths, and that would be 10 to 15. So we reduce all of them if we can. Well, I can't reduce 4/9, I can't reduce 3/8, but I can reduce 10/5 to being 2/3. Are any of these equal? No. So these are not similar. Now if we look at these two cylinders, I see a radius and a height. And we know that a radius can compare to a radius, and a height can compare to the height. So when I do that, I'm going to set up my proportions. So radius to radius, 12/8, is that equal to 18/12? Well, let's reduce. So the 12/8 can be divided by 4, so I end up getting 3/2. Is that equal to 18/12? Well, both of those reduced by 6 is 3/2. Yes. So yes, they are similar. Now, when I take into something like this, I have these two pyramids, I have a distance of one of the bases. We're told that they're square pyramids, for example, and I want to know some things about them. So I'm going to go ahead and assume that these two things are similar, and I want to know what the scale factor is, the ratio of the surface area, and the ratio of my volume. Now we've kind of seen this in the past when we talk about scale factor to ratio of area, and we did that on our last test. But now we're going to take it a step farther and go ratio of volume. So what I do for my scale factor is I take the two sides that I know that I'm going to compare, so this 6 and 10. So I'm going to go 6 to 10. Well, that can reduce. I can reduce both by 2, and I get 3/5. Now we know when we do ratio of area, all we have to do is square the scale factor. So I'm going to do 3/5 squared. So remember, the square goes to both things, so that's 9/25. Now the interesting thing about this is that although we say ratio of surface area, this is also true for my ratio of lateral area. So anytime that we're talking about area, whether it's surface area or lateral area, you just have to square the scale factor. The ratio of my volume is just going to be the scale factor cubed, right? Area, we talk about units being squared. Volume, we talk about units being cubed. So that makes sense why we would cube it. So I would get 27/125, and that's my ratio of my volume. Okay, so let's say I'm told that I have two square pyramids and I know their volumes. I know one is 64 inches cubed and one is 216 inches cubed, and I know that these two shapes are similar. So automatically, before I do anything, I already have my ratio of my volume. I can go ahead and say, okay, small is 64, and then the large is 216. And you can reduce that if you want, but we're going to keep this just like this for right now. Now, when I go and look at my scale factor, again, keep in mind that when we went from scale factor to ratio of volume, we cubed everything. So to go backwards, to go from volume to scale factor, all we have to do is take the cube root of both of these things. So going from here to here, we're going to take the cube root. If you were going to go from area to the scale factor, think about what you would do, right? You would just square root it. So I would see here that the cube root of 64 is 4, and that the cube root of 216 is 6. And so I can reduce that, and I get 2/3. All right. So if we had reduced our ratio of our volume, you would see that it would be 8/27. And that's exactly what we see here. 2/3 cubed is 8/27. So we can reduce our ratio of volume so that way that this becomes the ratio. And again, you would take the cube root of 8 to get 2 and the cube root of 27 to get 3. Now to go to the surface area, we know we just take our ratio, our scale factor, and square it, so we get 4/9. Now we can use this information to help us solve for problems, because if you're told of a specific surface area of one of them and the volumes of the other, you're able to figure out what the surface area is of that third one. Okay, so when I'm talking here, we have our volumes, we have the scale factor, ratio of surface area, and the ratio of our volumes that we just found from the previous slide. So now I'm told another piece of information. I'm told my surface area of my larger one is 16 inches squared, and I'm told that the surface area over here is something else. So I want to know if these relationships are true, what is the surface area of this smaller pyramid? So what we do is we set up some equations. So first we had to find from the volume, we went to find the ratio of our volume. Then we went to find our scale factor, and then we went to finding the ratio of the surface area. So now that I know that, I can say 4/9 is my ratio of my surface area. That has to be equal to something, which I don't know, because that's the surface area from over here. We're going to call it x, over 16. So now I can cross multiply and solve just like you would do in any kind of problem like this. So 4 times 16 is 64, and that has to equal 9x. Divide both sides by 9. Those cancel out. So I get 64/9, and that can't reduce at all. So this would be my surface area for my smaller pyramid.